With our two eyes, humans have the ability to judge depth with precision of about a millimeter at the range of a meter or two. And while our brains aren't computationally developed enough to be able to calculate the exact distance, we still are able to use that information with our depth perception and be able to reach out and grab things that are in space. And by in space, I mean in 3D space. We're not gonna just grab a satellite from orbit. Point being, our eyes use triangulation to figure out how far away things are from us. Triangulation just means using two known angle measurements separated by a known baseline distance b, as well as some trigonometry to determine how far away something is. But here at the Optics Lab, we've developed a triangulation device that can get nanometer scale precision at the range of a few meters. Remember that a nanometer is a billionth of a meter, so this system is 1,000,000 times better than our eyes are. At least at measuring depth, that is. Notice how I said precision and not accuracy. That's because in science, precision and accuracy have very different meanings, even though they're generally in the same category. Precision is how confident we are in a measurement. If we have a bunch of decimal places after a measurement, that means it's a very high precision measurement. But accuracy is the ballpark that the measurement is in. Imagine you're doing archery and all of your shots are missing to the left of the target and they're not closely grouped together. That's both imprecise and inaccurate because your shots aren't closely grouped and they're off of the target. If your shots aren't closely grouped but are in the center of the target on average, that means you have an accurate measurement. It's just your precision needs some work. If all of your shots are hitting a specific area of the target that's not the center, that's an inaccurate measurement. But it is precise. But what we want in science is both precise and accurate. That's all of your shots hitting the same small circle in the center. Because precise measurements mean nothing without the accuracy in knowing that they're in the right place. If we have two cameras separated by a known baseline distance b, we can use a light source's placement on the sensor to figure out roughly the angles of where the things are relative to the camera. Using some trigonometry, really just the tangent, we can figure out the distance z relative to b and the angle phi. With two different values of phi, the equation looks like this. But if the values of phi are the same, we get this simpler equation. So it turns out there's a fundamental bound to how low we can get our uncertainty of these measurements. To get the uncertainty of z, we take the differential, which I'm not going to bog you down with the details of. When we do the math and rewrite in terms of z, we get this equation here, which says that the uncertainty in z equals the uncertainty in b times z over b minus the uncertainty of phi times b over 2 plus 2z squared over b, all in parentheses. Now, if we're very confident that the uncertainty in b is very low, which means it's a both highly accurate and highly precise measurement, then we can kind of ignore this first term. What's important is the part here in the parentheses. When b is much smaller than z, that means our uncertainty in z scales quadratically with the measurement of z itself. So if the distance to the thing we're measuring is twice as far away, that means we have a 4 times worse uncertainty value. So as things get further and further away, doing triangulation becomes more and more difficult. But the key is that this quadratic scaling of uncertainty is relative to the uncertainty in the angle measurement, which means that if we reduce the uncertainty of the angle measurement, we can reduce the amount that the quadratic scaling matters. But because of the way light works, there is actually a fundamental limit to how small this uncertainty can get. Here's my advisor and the author of the paper that this video is based on talking more about that.
If we had a perfect focus so that light completely came down to a point, we could know exactly the direction to that point source. But we can't do that because what really falls on the detector isn't a perfect point, but it's called an airy disk. And that airy disk basically says, well, if I have photons falling on it, I could have a photon that arrives here, and a photon that arrives here, and here, and here, and here, and here. Really, the centroid is what we want to know. So we're trying to estimate the centroid, or the arrival of where these photons are coming from. You can never perfectly know what the centroid is. You always have some uncertainty in your centroid, and that is fundamentally limited by these photon statistics. We can model the amount of information in this using the Fisher information. Instead of having an airy disk, what we're going to model that as is a Gaussian. Just like a sphere is easier to model than a cow, a Gaussian is easier to model than an airy disk. So instead of having a little airy disk here, we're going to say that we have some sort of Gaussian like this. Sigma here is equal to lambda f over d, where lambda is the wavelength of the light, f is the focal length, and d is the diameter of the lens. So this light comes in, and then it comes down, it focuses, and you get some sort of Gaussian distribution. Suppose I have another source out here. Now, if I look at this, and I draw a line out here that goes like this to my detector, what this is going to do is this is going to create a new Gaussian on there, and this is going to have an angle here. What we're trying to do is find out what is the uncertainty in that angle. And that comes down to what's called the Fisher information. The Fisher information for finding D is basically a measure of how much information can we get about this particular parameter, in this case, the distance away from the optical axis on the camera. And that is given by I is equal to n over sigma squared, where n is the number of photons and sigma is the width of the Gaussian. So this ends up giving us the Fisher information for that. Now there is something called the Cramer-Rao bound that basically says how well you can know the uncertainty of something, or the variance of some parameter is going to be given by the inverse of the Fisher information. And so what we can say is the square root of that basically says that the best I can do, delta phi, is going to be greater than or equal to lambda over square root of n times d. So all we did is take the inverse of this and take the square root. And this basically tells us that the best that we can do under any circumstance, given this and the fact that there is a photon statistics, is this lambda square root of over square root of n times d. So I did numbers here. So I said, let's suppose our wavelength is 500 nanometers. Diameter is 1 inch. We're receiving 1 microwatt of light. Delta phi is approximately 10 picoradians per root hertz, which means that if I measure this signal coming in for 1 second, I should get about 10 picoradians of uncertainty.
With typical cameras, we have about a 2 micron pixel, and we can get about 0.1 pixel precision with the Gaussian approximations. The problem here, of course, is that cameras are digital, so we can only get that 0.1 pixel precision. If those pixels were 10,000 times smaller, or somehow we could get 100,000th of a pixel of precision, then maybe we could get close to that fundamental limit. But the reason we can't get that close is because of the way that the digitization of the image works. Since a camera provides a digital signal, there's lots of noise introduced into that, which means that the best camera systems these days get about 73 microns at the 1.4 meter range, which isn't nearly as close as we could theoretically be, and furthermore isn't anywhere close to the system that we've developed. So we can't use cameras to measure an angle so precisely. So what do we use? Well, since the problem is the digital signal, we have to use some kind of analog detector.
The standard technique is to use a camera with a CCD array and doing sub-pixel resolution on your camera. What we're doing is a little bit different. What we have is a lens and 2 detectors. What they do is they take the light coming in, and as you recall, we have some sort of Gaussian distribution in light. If a star is perfectly aligned with the centroid of this, then what you'll find is, on average, you're going to get half of your photons here and half of your photons here. Now, because we're dealing with photon statistics, sometimes you're going to get more over here, sometimes you're going to get more over here, which means you're going to get some uncertainty in the centroid position. However, because we're doing this and we're preserving all of the analog information that is contained in here, then all of that analog information contains, we haven't digitized our signal, which loses Fisher information. We retain all of the Fisher information. We difference that voltage, and then we take it up to for processing. Now, when we're dealing with triangulation, what we then do is we have 2 of these. We difference those values, and then we come and we difference those values again. So we keep everything analog. Then only after we've differenced them, we run those through a gain and then we, so that we amplify the signal, and then we digitize the signal.
Based on the Gaussian approximations that Dr. Howell has talked about, we can figure out the distance that the airy disk has moved on the sensor, and thus the angle. And because of the analog signal, we get a much higher precision read of this. So we take the two differences from our two balanced detectors and figure out the difference of those, and with that number, we then send that to the computer to do the calculation. Since it's analog signals being subtracted instead of digital ones, we get a much clearer picture and much higher angular sensitivity. If this measuring device were measuring something on the moon, for example, here from Earth, it would have precision of about 4 millimeters on the surface of the moon, from 400,000 kilometers away, which goes to show how precise these angle measurements can be. Putting two of these balanced detectors together into a single system and using them instead of cameras, we have a much smaller angular uncertainty and thus a much smaller depth uncertainty. So using those balanced detectors, we've created the device that can do exactly that. It can get nanometer scale precision at the distance of a couple meters. That's 1,000,000 times better than what our eyes can do. So with these incredibly precise angle measurements, we do have a bottleneck now. And that's the setup of the device in general. If we aren't able to have precise angular control of these sensors, we don't know the angles they're positioned at, and so our accuracy could be way off if we miscalibrate it. But fortunately, we have these angular rotation stages, which allow you to set it and forget it when it comes to calibration. If you want to set it for a certain range, you adjust the angles, adjust your code a little bit, and leave it at that. Now you may have noticed that I said code, and yes, I did. That's because we're running these with Raspberry Pi with Python. Raspberry Pi is a relatively low-end operating system, but that means it has huge benefits. First of all, it's very accessible, both monetarily and with ease of use. And given the 26 input and output pins, we can connect whatever scientific devices we want to it without having to mess around with a USB interface or anything like that. Now, you could run this kind of device on any kind of computer you wanted, but the Raspberry Pi makes sense for our use case. Those 26 I/O ports can be used to control anything from an LED to a stepper motor or to read data from a sensor like the one we have. So we can plug in pretty much anything we want and do science directly on this computer. We can program the Raspberry Pi to do what it needs to do with the inputs from these sensors. So getting the measurements of the differences and using that to figure out the angle measurements and then using the tangent to figure out the distance. It doesn't take much computing power. In fact, a lot of this could be done by hand with the help of a calculator. You're probably curious as to what this device looks like, so here's Levi to talk about his progress on the project so far.
So the first thing I had to do was to get the platform and the carry to rotate. So I needed to fire a stepper motor a bunch of times, 60,000 rotations of the stepper motor to fully do a rotation. We don't need that much. We only need about 4,000 to pivot it about like 1/8 of the way. For the carry, I'm mainly just using it to adjust the LED distance to make it more accurate. After I got those two dialed in, I then had to turn on cameras and get them to measure distance to an LED. I essentially just placed my phone across the room. Then I took a picture with the cameras and I used a formula to calculate the distance from the middle of the cameras to the brightest pixel on the picture the cameras took. I then moved to the sensors.
But the thing is, our sensors output an analog signal, whereas Raspberry Pi needs a digital signal to be able to work. So we do have to use a 24-bit analog to digital converter to get the data into a processable, usable form.
So the first thing I did was I turned on just the left sensor to make sure that the ports of the analog to digital converter were working correctly. At first they were not, so I had to get a new analog to digital converter. Once I made sure all 4 ports were working, I then used the second sensor. I have been attempting to dial in a perfect displacement of the two sensors so that way they are perfectly angled at the LED. So that way when I calibrate it, I can see roughly where the distance is and I know what it should be, and then I can continue adjusting very fine points of the sensor angle to where we have a good way to calculate distance via the sensors. So first off, this metal bar is mounted to the stepper motor, and when I turn the system on, it will turn this about 15 degrees to the right clockwise, or to the right, and then it will reset to where it is right now, and then it'll turn it about 15 degrees to the left, so that way it can capture an accurate distance to the brightest pixel. Currently I have the sensors angled to the brightest pixel just so that way it starts at 0 and ends at 0 in the measurement. These cameras are just kind of showing generally what is being seen by the LEDs by taking a picture and essentially cutting it in half and sticking the two halves of the picture together. And that should be roughly, the LED should be roughly in the middle of that picture. Then currently this is completely stationary in the program. I'm moving it back and forth separately, but once I get the distance very accurate with the sensors, I will begin to have a program move this back and forth, and then the sensors will calculate the distance, like the change in distance. And then eventually I'm going to angle this by a certain degree so that way we can capture not just the general distance from between the two sensors, but we can calculate the distance in the X direction and the distance in the Y direction displacement wise.
Since we're doing all the differencing while the signal is still in its analog form, we do not lose that analog information. And so the Fisher information of the system is preserved. Since all of the Fisher information is preserved, the fundamental lower limit is very close to how far we've actually gotten.
I want to point out, what we're doing here gives us 4 or 5 orders of magnitude better resolution than what is currently done with cameras. Given that that is the case, let's think about this in terms of space applications. For example, navigation. One of the things that they do is they have like a star field, right? You have a bunch of stars out here. They have all these known maps stored in an array. And what they can do is they can say, oh, I see all of these stars over here. I'm able to get some good estimation of where those stars are. I can correlate that with a map and therefore get my orientation. But it's intrinsically limited by your ability to determine the positions of those centroids. And that uncertainty creates an uncertainty in your orientation. What if you want to know the distance to an object? So then what they have is they have a couple of these cameras. And if you have an uncertainty here that's quite large, then if you have objects that are really, really far away, it's completely useless because the uncertainty here is so large that by the time you get to tens or hundreds of kilometers or thousands of kilometers, the uncertainty in length is so enormous that they just basically throw out. They just say, we can't even find it, so we're not even going to try to do triangulation. And so you have to have multiple satellites with really long baselines, and those really long baselines are trying to establish this. And what I'm saying is that if we have a single satellite with 2 really highly precisely aligned of these detectors that we've been focusing on, then we can get extremely accurate positions even up to 1,000 kilometers away.
So to summarize, triangulation is using 2 angle measurements to get a distance measurement away from something. And you can use 2 cameras to do that. But because of the way the uncertainty works in triangulation, for really far distances, it doesn't work very well. But if we can reduce the uncertainty of our angle measurements, we can reduce the uncertainty of the distance measurement by a lot. So to improve that uncertainty, we can use analog detectors instead of digital cameras. Those analog detectors preserve what's called the Fisher information, which is how much information is stored within the photon statistics. Since we preserve that Fisher information, we can get a better angle measurement uncertainty. And so by improving that angular uncertainty, we can get very close to the fundamental limit of a triangulation system. Anyways, thank you for tuning into the Optics Lab. I hope you enjoyed or learned something. You can check out the paper that's been published in the description, and make sure you drop any questions you have in the comments below. Until next time, I've been Patrick, we've been the Optics Lab, and we hope you enjoyed.